So thank you, Sarah, for the introduction, and welcome everyone to the GO-BGC workshop, Building a Community of Biogeochemistry Float Data Users. I'm Ken Johnson. I'm a senior scientist at the Monterey Bay Aquarium Research Institute. I'm the lead principal investigator for the GO-BGC program. I'll introduce the rest of the team in a bit. And I'm also co-chair of the Biogeochemical Argo steering team. Let's see. So following on Sarah, I just want to thank the sponsors of the workshop, OCB, US CLIVAR, and in particular, I want to thank the funders of all of this work. NSF, as you'll see, is funding the GO-BGC program, but the biogeochemical Argo efforts in the US have also received significant support from NOAA, from NASA, and from the David and Lucille Packard Foundation. And all of this is built, on a foundation laid by the Biogeochemical Argo program, and that in turn is laid on the foundation of the Argo program. And I think we have a great deal of thanks to give to the people that had the foresight to really lead those programs forward. One quick shout out to the workshop committee, coming from the GO-BGC executive team and led by Steve Reiser, who was chair, but Andrea Fassbender, Allison Gray, Todd Martz, George Matsumoto, Rue Nicholson, Yui Takashita, Roberta Hatinsky, and Mariah Salisbury all, put an extraordinary amount of work in. And as Sarah said, there will be data tutorials. So a key to the success of this workshop is building a bigger community of users and enabling just, routine access to the data system is key to that. And this team of people have contributed code and organization and will run the workshops. And I think they have done just an outstanding job. Allison Gray, Andrea again, Ethan Campbell, Hartmut Frenzel, Rue Nicholson, John Sharp, Eben Wong, Warren Kornick, Rafaela Sauzeda, Catherine Schmechtig, Quentin Jutard, Josh Plant, Tanya Maurer, Yui Takeshita, Ryan Anderson, Katie Christensen have all contributed code or helped in one way or another, and I really want to thank them. So let's see. So this is presumably you're here because you're interested in the operation of biological and chemical sensors on floats, downwelling irradiance, chlorophyll fluorescence, optical backscatter, oxygen sensors, nitrate sensors, pH sensors. If you're not here because you're interested in that, you've joined the wrong Zoom session, and you probably can leave now. But the focus is on biological and chemical sensors on floats. A very brief outline of the talk. I'm just going to briefly touch on change in the ocean and the role of the Argo array in observing temperature and BGC Argo observations in the ocean. Planning for a global biogeochemical Argo observing system, and then implementation of the GO-BGC array project. This is the major US contribution to a global BGC Argo observing system, and the role of the US and the international community in sustaining this system. And really, again, the theme through all of this is expanding the community of users. So we know the oceans are warming. A paper by Li Jing Cheng, one of many papers looking at warming of the ocean, has this very nice plot that shows time on the bottom. The ocean heat content anomaly in zetajoules, which is a hard unit for me to come to grips with, but the right-hand axis shows warming in degrees Kelvin on the right. The middle panel shows the record of observational record of warming in the ocean. It goes back to the 1960s, and the error bars are quite large early on, get much smaller. This is the reduction in the error bars is the contribution of the Argo array. And then they show the predicted warming going forward. RCP 8.5 from the CMIP model ensemble now appears to be a very likely trajectory going forward. And, we see changes in the ocean today due to the warming. The modelers predict much greater warming going into the future. This has distinct impacts on the ocean. So the Argo array has really revolutionized our ability to observe these kind of changes. This is a review paper just out recently, an annual review of marine sciences led by Greg Johnson, but a series of authors from the Argo steering team. And this figure from the paper shows the number of profiles per 1 degree by 1 degree longitude and latitude bin. The color scale is the number of temperature profiles that go to at least 1,000 meters in each of those bins. This plot shows all of the ship-based profiles, basically the last 100 years that are available in the National Oceanographic Data Center archives. Much of the ocean, there are large parts that have had no temperature profiles, and much of the ocean are these black and blue dots where there are only 1 or 2 profiles in 100 years. Hard to observe change if we aren't observing the ocean. On the other hand, the Argo array has turned the similar map red and purple with dozens of profiles in each bin over just the last 21 years. Really has revolutionized our understanding of ocean physics. And at the same time that Argo has been observing ocean temperature, there has been a push to add chemical and biological sensors to profiling floats. A phenomenal number of papers have come out of these, reasonably small numbers of profiling floats in many of these studies, 2, 3, 4 dozen floats. Many of the papers show a subset in very high profile journals. The number of publications per year is going up exponentially. We know that chemical and biological sensors on floats can transform our understanding of the ocean. They can operate successfully in small arrays, has really contributed to our understanding of a variety of ocean biogeochemistry topics. And so again, a figure from this review paper by Greg Johnson et al. This is the Northeast Pacific Ocean near Ocean Station Papa, vertical depth down to 500 meters and time 2006 up to the present. And we see a phenomena that became known publicly in the public literature as the warm blob in the North Pacific in 2014, 15, and 16. This paper, this phenomenon, the warm blob, had phenomenal effects. It rippled through plankton productivity, zooplankton productivity up to fisheries, ultimately led to a massive die-off in seabirds. A blob of hot water killed 1 million seabirds. This was a paper in PLOS One. And at the same time, there was an array of profiling floats with nitrate sensors operating in this region, all deployed again at Ocean Station Papa. And a paper by Mariana Biff et al., a loss of resilience in organic carbon production. They looked at the heat content. So this is time 2010 up to 2018, temperature, nitrate, and from the nitrate concentrations, we can infer net community production, the amount of organic matter produced by the community. And in the first year of the warm blob, when you see the highest temperatures forming, nitrate gets drawn down, and we actually have an enhancement of productivity in the North Pacific. But the second year following that, which was associated not only with the warm blob, but an ENSO event following on after that, we have a crash in productivity. And Mariana and her colleagues would argue that it's multiple years in a row of these warm events that lead to a disconnect between the mixed layer and nutrient stocks in the deep ocean that lead to productivity. Well, we know the ocean is going to warm. We can anticipate more events and multiple year strings like this that will have severe effects on the ecosystem. There will be changes in wind, changes in ice, ocean acidification, changes in oxygen, all of which can be observed by profiling floats. And so the success of floats in doing science projects like this have led for over 10 years now to planning to extend BGC Argo to a global array. As up to this time, it's been mostly operating as relatively small science-driven projects and not a large, essentially operational system. First program led by Nikki Gruber in 2007, the Argo Oxygen Program. Ocean OBS had a number of studies, biooptical profiling floats in 2009, and OCB in 2009 sponsored a workshop observing biogeochemical cycles at global scales with profiling floats and gliders, prospects for a global array. One of the conclusions of this workshop was that the next step was to go from smaller scale arrays to a regional system, and that led to the Southern Ocean Carbon and Climate Observations and Modeling Program. Led by Jorge Sarmiento at Princeton. This started in 2014 with NSF funding. It's completed 6 years of operation, deployed 204 floats into the Southern Ocean, floats with oxygen, pH, nitrate, and biooptical sensors. More than 120 publications have come from this, been extremely successful. It was renewed for 4 more years, and an additional 120 floats. Clearly shows the community's capability to operate at a basin scale, successfully running a large number of floats. The success of SOCOM led to planning, again, a renewed planning for a global array. One of the essential questions is how many floats do we really need? And various assessments published suggested about 1,000 floats spread globally would greatly reduce uncertainty in biogeochemical processes, would transform our ability to understand chemical and biological cycling in the ocean. Those assessments, by the way, have been reinforced by recent publications. For example, this paper just came out in 2021 in Biogeosciences by David Ford, finds that 1,000 floats brought clear improvements in all assimilated variables in a global ocean model. Suggested that while 1,000 floats brought great improvement, even more floats would provide even more improvement. Another paper, an observing system simulation for Indian Ocean surface PCO2, found one may consider that around 20 bioargos are the right choice. Extrapolated to the globe, this would imply maybe 400 floats. It's a number, but in general, they are finding that the 1,000 number seems to lie in the middle and be a reasonably robust estimate of what we need. So in 2016, there was a meeting to develop an international plan for 1,000 profiling floats with oxygen, pH, nitrate, biooptics. The US would provide half of those floats, as in core Argo. You will hear throughout this workshop a discussion of the processes that can be observed: carbon cycling, oxygen minimum zones, nutrient flux, acidification, the biological carbon pump, phytoplankton phenology, primary production. We can manage in a much more effective way living marine resources, carbon budget verification. We can improve operational ocean models. And key to all of this, the data is freely available to everyone in real time. So as an outcome of that workshop, a group of scientists in the US wrote a proposal to the National Science Foundation for the Global Ocean Biogeochemistry Array. And in October of last year, NSF made a 5-year award for the GO-BGC array. That award will fund 500 profiling floats distributed globally. The floats will carry oxygen, nitrate, pH, biooptics. Partner institutions are the Monterey Bay Aquarium Research Institute, the University of Washington, Scripps, Woods Hole Oceanographic Institution, and Princeton University. So key to this program was funded by the Mid-Scale Research Infrastructure Program at NSF, the National Science Foundation. Ironically, the Science Foundation, the Mid-Scale RI2 program, will not support proposals that include science research. That sounds somewhat ironic, but the fact is this is building a facility for the community to use, much like building a ship. Our job now is to bring users to come and use this facility, and this really is the goal of this program. the GO-BGC array will not be successful unless people use it for science research independent. So I want to make the point that the group that led this proposal, we did not receive large funding for postdocs, graduate students, research. The group that wrote the proposal for this array are convinced that this is the route we need to go to improve our understanding of the ocean. Steve Reiser, Lynn Talley, Susan Wafels, Jorge Sarmiento, Heidi Cullen, Yui Takeshita, George Matsumoto, Andrea Fassbender, Sarah Perkey, Todd Martz, Allison Gray, Rue Nicholson, and Roberta Hatinsky. We didn't do this to enrich our labs in science projects. We will use the data, but we view this as we're committed to providing this as a facility for the ocean community. And the goal of this workshop is to build that community of users. So the primary goal is to build a 500 float global array, evenly distributed with internet, considering international contributions. If, for example, the EU wanted to populate the North Atlantic, we would put more floats elsewhere. It should be sustainable with a replacement rate near 125 floats a year, which is based on a mean lifetime of 4 years. Floats should operate more than 4 years, but there are inevitable losses. The average lifetime will be closer to 4 years. To achieve this, the floats have to have a cycle time of order of 7 to 10 days. So every GO-BGC is an Argo float. The data are all freely available without restriction in real time. But please acknowledge Argo and GO-BGC if you do use the data. Sarah showed some of the statistics for the workshop. Again, a large number of early career scientists. When I downloaded this, 348 registrants, about evenly balanced for gender diversity, a broad ethnic diversity for the workshop. People interested in a variety of languages. I should note that when we started planning, we assumed it would be MATLAB and Python. When the registrants showed that there was a large interest in R, there was a big scramble to add R to the tutorials. And as Sarah pointed out, much over half of the participants are really new to the Argo system, and this is great. This is building a new user base. As Sarah also said, 25 nations. So the ocean doesn't recognize national boundaries, and I don't think that the GO-BGC array really should operate that way as well. So remember, the data is freely available to everyone, no matter where you are from. About half the users at this workshop are from the U.S., but the other half are from the world, and this really is excellent. GO-BGC will be, by its very nature, it will have to be an international program. The GO-BGC does not have ship time. So this, as in SOCOM, floats will be deployed by ships of opportunity, people that very kindly make their ship time available to us for float operations. SOCOM already has used ships from Australia, Germany, India, Japan, South Africa, Switzerland, the United Kingdom, as well as United States research vessels. As GO-BGC moves forward, this will be key to our success. Another comment that I frequently hear is that GO-BGC, do we intend to replace ships and satellites to observe the ocean? And the answer to that is absolutely not. I think biogeochemical Argo is a nexus in ocean observing, but it doesn't replace ships and satellites. It makes a merged data set more powerful. It extends satellite observations into depth, but can't match the high resolution of satellites. It extends ship data in time, but can't match the versatility, the variety of observations made on ships. It can only extend a core set of measurements. But by operating in the middle of all of these systems, we will have a much more powerful observing system that unifies all of these systems. You'll hear about outreach. So to sustain the system, it's expensive. We have to build public understanding and support for the systems. There are a broad range of outreach activities in GO-BGC that you will hear about, from a robotic challenge, which involves students in high school and college and middle school building profiling floats to an Adopt a Float program, educator workshops, this research workshop, and a makerspace at Scripps to teach students about sensors and building observing systems. So there are a variety of challenges. We have to scale up float and sensor production from essentially a small research scale to much more of an industrial scale. This is not a trivial task. Long-term operation is needed to detect climate signals. So GO-BGC is funded as a 5-year proposal. If we are going to be really successful in observing long-term climate signals, we need to operate more than 5 years. It will have to be renewed, which means that this first 5-year program really needs to be successful to ensure continuation. To be successful, we need a broad community of users that, and use the data that support the system that will want it to be continued. And that means that high quality data must be easily accessible. And that really is a key part of this workshop. So you can't put 500 floats into the ocean all in one fell swoop. GO-BGC, the plan was to do 56 floats in year 1, building up to a sustainable rate of 125 per year in the future. COVID-19 has totally messed all of this up. The SOCOM program, as an example, doing 30 floats a year for the next 4 years. In the year 2020, we could not get our floats into the water, many of our floats into the water, so we have a carryover of 27 floats. SOCOM actually has also 57 floats this year, but we'll have a hard time getting those deployed. We'll have a hard time getting the 56 built, all because of float production. These will carry over into subsequent years. But these floats are all funded. They will go into the water. One of the consequences of that is that right now, GO-BGC has 11 floats operating in the ocean. It's a relatively small array in the Western Atlantic, but I want to make the point that U.S. Argo programs have 166 floats now operating with a much more of a global distribution. That data also processed through the same chain that GO-BGC will use, equivalent quality and available, and all of global BGC Argo. Again, these floats are all Argo. They're all publicly available. We're starting to build a nearly global array, 411 BGC floats in the ocean. I should make the point, though, that this 400, we're not 40% of the way done to 1,000. Many of these floats do not carry the full sensor array that we want. For example, today in the ocean, only 159 of the operating Argo floats have nitrate sensors. So you might say we're only 16% of the way done with nitrate. Radiometers, only 62 of the floats are operating today with radiometers. We're only 6% of the way done. So GO-BGC will have a significant impact. But today, this data and the tools that you will learn about and the science that you'll hear about are all doable with all of these floats. So there is an impressive amount of data out there. This looks like a lot. We want it to look like this. 500 US floats, 500 more international floats operating for an extended period of time. So how can you participate in GO-BGC? Well, first of all, as I said, GO-BGC does not have ship time. Tell us about deployment cruises. Help us coordinate float deployments internationally. Lynn Talley will speak more about that, but we will be dependent on the international community to get floats into the water. Analyze data, write proposals, communicate your interest to funding agencies. If we want this to be successful and to continue, we have to build a community of users that are using the data and doing novel things. So develop novel applications, integrate the data into fishery models, for example, carbon budget validation verification, and outreach. Link GO-BGC floats with the school, communicate to the public on the importance of this system. And so I have just 2 more slides left. I hope I'm on time, reasonably close. Often people ask, my gosh, you're putting floats in the ocean. It is causing a pollution problem. There has been a lot of effort to assess this. There's a very nice report led by Steve Reiser and Susan Wafels on the Argo website, and this report has been turned into a nice pamphlet that looks at the impact of the environmental impact of Argo floats. It is quite small, and I will close by then making the point, even so, there is an impact. Why are floats not recovered? And if we just look at the scale of the problem, a global class ship that can transit into the open ocean, particularly the Southern Ocean high latitudes, and recover floats will actually burn about 10 tons, 10,000 kilograms of fuel a day, versus a float that weighs about 30 kilograms. That global class ship, although it looks like a lot of floats in the ocean, would still take at least 2 days to recover each float. And if we look at the environmental impact, in terms of many variables, but just pick protons. The ship burns fuel. About 25% of the CO2 emitted to the atmosphere will enter the ocean, and a global ship that recovered 125 floats a year would probably end up adding about 10 to the 7 moles of protons to the ocean. Whereas when 125 floats decompose, it's about 4 orders of magnitude less impact. We would argue the knowledge gained will result in understanding and modifications to environmental policy that will really outweigh the modest impact of the array. And so we are going forward with building a system that we think will really transform ocean science, but this is only going to happen if the community really gets involved and supports the program. And so with that, I'm done. Thank you.